So hello students, welcome to BVLSI online lecture 45B. So we are going to continue with solving of CMOS inverter numericals. So last time we have solved one numerical on symmetric CMOS inverter. Today let us see the other category. So write the numerical statement for a CMOS inverter. The value of Kn is given as 100 microampere per volt square. Kp is given as 15 microampere per volt square. Then VTON is 1 volt. VTOP is minus zero point -0.8 volt and supply voltage is 3.3 volt. So we need to calculate first case all the four critical parameters, that is VOH, VOL, VIL and VIH. Secondly, we need to calculate the noise margin levels. So pretty straightforward. Noise margins. Okay. So let us start. So from the given data, let's start by calculating KR first. So KR is inverter ratio, which is given by Kn by Kp. Here it is 100 divided by 50, which is coming out to be 2. So KR is 2. So basically, and VTON is not equal to VTOP, right? VTON is not equal to VTOP. So it's an example of a not a symmetric CMOS inverter. So asymmetric CMOS inverter. So that means we have to use the regular formulas which we have derived in the class last time in 44B. Alright. So but first of all, two parameters we can quickly calculate. Which are the two? First one, this is first. VOH we can easily calculate. It is equal to VDD. So at least write this and come. You will get some marks for KR writing, calculating the value of KR, then VOH, and finally VOL is 0. So at least this much you attempt and come. Then next is finding the value of VIL. Now this I'll explain you as a trick. How to calculate VIL basically. Okay. So first of all we have to use the formula. What was the formula? Let me help you out with the derivation, reference to the derivation. This was the derivation for VIL, right? And at the end we got one formula. This formula we will be using it. This one, VIL. It's twice V out minus VDD plus VTOP plus KR into VTON divided by 1 plus KR. So let us write this formula down. That is V in equal to VIL, which is V in also, right? So we can write here as VIL equal to V in, that is same as V in, equal to, let us write down the formula, twice V out minus VDD plus VTOP plus KR times VTON divided by 1 plus KR. Alright. So let's substitute the values now. We'll use the term as V in only, and at the last step we'll calculate V in equal to VIL. Okay, so VIL is associated with V in only, don't worry about it. Alright, so let's continue this further. Alright, so we can write this as V in equal to, we don't know the value of V out, right? So we write as it is, twice V out minus VDD is 3.3. VTOP is how much? I think it's minus 0.8. Correct? It's minus 0.8. KR is 2. So 2 into VTON is 1. So 2 into 1 and divided by 1 plus 2. Alright, let's solve this further. That is V in is equal to twice V out minus 3.3 minus 0.8 plus 2. How much it is? Quickly tell me. 2.1. divided by 3. Okay, so let us rearrange this in the form that we will be solving V out in terms of V in. So calculate V out in terms of V in now. Okay, so here you will get twice V out will be equal to 3 times V in plus 2.1. Okay, that is V out is equal to 3 by 2, that is 1.5 V in plus 2.1 divided by 2. How much is 2.1 divided by 2? I think 1.05 plus 1.05. So this is the equation which we are getting. Okay, let's call this equation number 1. Understood? Have you completed up till here, everyone? So we have got one equation of V out in terms of V in. Now we have to solve using another equation. Students, have you all completed up till here? Alright. Now for the next step, see, listen, we cannot remember this big formula. Okay, we have to just remember that when V in is equal to VIL, let me show it to you. So next we will continue this. We'll be using a big formula. So just a background which don't need to remember the formula. This is just the background which I'm giving it to you. At V in equal to VIL, just remember, just draw the small VTC curve and let us jog our memories. So the output VTC curve, it's like this, and where is my VIL? VIL is over here. So for V in equal to VIL, my output is just almost equal to VDD. Okay, so that means my VDSN is almost equal to VDD, and my VDSP, which is V out minus VDD, it is almost equal to 0. Okay, so this means that my NMOS transistor is in saturation. You have to remember that. And this means that my PMOS transistor is in linear region. For VDSP, if it is almost equal to 0, let's consider that. Yeah, PMOS is in linear and this NMOS is in saturation. Yes or no? So we have to remember this. Also, for a CMOS inverter, if we draw it, I mean, this is the trick I am telling you to not to remember the formulas. So if you don't remember the formula and still follow this technique, this will be fine. It will take a minute to recollect, jog our memory. So what are the 4 constraints which we have found out related to the CMOS inverter? So write them down. That is VGSN is equal to V in, VDSN is equal to V out, then VGSP is equal to V in minus VDD, and VDSP is equal to V out minus VDD. So these 4 constraints we have to substitute in the formulas which will come next. Now we have to equate IDP linear equal to IDN saturation. So let's write down the formula. So IDN linear formula, what it is? Can you let me know? Kp by 2 twice. Yeah, what will come over here? VGS P minus VTO P the whole square into VDS P minus VDS P the whole square, right? And here what will come? Kn by 2 VGSN minus VTON the whole square. You need to practice this. Now, wherever you see these terms, VGSP, VDSP, you have to replace it with these formulas which we have used over here, right? And if you do that, you will arrive at that equation which we are ready to solve now. So this 2 and 2 will get cancelled, and we substitute Kr equal to Kn by Kp. So this Kr will go over here. So at the end, what you will get is twice VGSP is V in minus VDD minus VTOP the whole square. VDSP is V out minus VDD, V out minus VDD minus V out minus VDD the whole square. I mean this we keep it over here. Uh, yeah, the whole square, no need for this, and that is equal to KR. Okay, KN by KP is KR, and what is VGS and Vin? So Vin minus VTON. Are you understanding? So we get this formula. Now this is what we will have to use now. Remember, this is the same formula which we are getting over here now. See, twice Vin minus VDD minus VTOP square. See this? Oh, VTOP actually it is not square. Sorry for that. Yeah, Vin minus VDD minus VTOP into VDD minus VDD, V out minus VDD, then minus V out minus VDD the whole square is equal to KR. See this, I'm showing you all to just to show you all it's equal to 2.1. So this is how you write this formula, by writing this few steps. So no need to remember this formula for shown over here. Okay, yes or no? Now what do we do is, wherever we have got equation number 1, what is that equation number 1? 1.5 times V in plus 1.05. So wherever you see V out, we substitute in this equation. This equation, this yellow color box. Okay, and this I call it as equation number 2. Alright, so what was equation number 1? V out equal to 1.5 times V in plus 1.05, right? This was equation number 1. Now you consider this, and now wherever you see V out, you have to substitute this equation 1.5 plus 1.05. Okay, so have you understood this step, or you have any doubts? Yeah, so let's solve it now. Now it's delicate. Now we have to do it one by one. Let's do it. So be very careful now. Okay, let me I'm giving you all time so that you can write. So this you derive it in 2 steps, no problem at all. So let me start now. Twice, wherever you see V out, wherever you see V out, substitute this value. So here is the V out terms, replace it by this. So it is V in minus VDD minus VTOP into 1.5 times V in plus 1.05 minus VDD, again 1.5 times V in plus 1.05 minus VDD the whole square, and that is equal to KR into V in minus VTON. Alright, be very very careful. Now we substitute all the values, that is twice, okay, that is twice V in, what is VDD, VTOP, what is VTOP? Minus 0.8, right? So minus minus this become plus 0.8. Then here we have 1.5 V in plus, this is 1.05 minus 3.3. Here again 1.5 V in plus 1.05 minus 3.3 the whole square. KR is 2, right? So 2 times V in minus 1 the whole square. Okay, understood this? So we'll absorb this 2 over here in this the first bracket. So what do we get inside? What do we have? 3.3 plus 0.8, how much it is? I think 2.5, na? Minus 2.5. So if you put it inside, you will get twice V in minus 5. That's it. The first term is done. Now the second term will come. How much it is? 1.5 times V in minus, how much is this? 3.3 minus 3.3 plus 1.05, how much it is? 2.25. So 2.25 minus 1.5 times V in minus 2.25 square is equal to KR. That is 2, right? That is twice V in this A minus B the whole square. So A square minus 2AB plus B square. Here it is. Understanding now? You all are with me? Hello? Now we open these two brackets. These two will solve it together. So how much is this? Can you tell me? 2 into 1.5, that is 3 V in square minus 5 into this thing 1.5. How much is that? 2 into 2.25, that is around 4.5 times V in, then minus this 7.5. I multiply these two, and then plus 5 into minus 5 into minus 2.25, that is 11.25. Just check this. I opened the bracket. So 3 into V in square minus 4.5 V in minus 7.5 V in plus 11.25, right? Now I open this bracket also. This is A minus B the whole square. So what I will get? A square, which is 2.25 times V in square minus 2AB. So 2 into 1.5 into 2.25. How much it is? 6.7 times 6.75 V in plus 2.25 square, which is 5.0625. Please check this. And this will be twice V in square minus 4 times V in plus 2. Plus check if I am done this correctly or no, because this is where the numerical is going to go ahead or no. Please check each and everything. I might do a mistake over here, but you need to be vigilant. Is this correct now? Yes or no? No, I'll club all the terms together. This is V in square term, this is V in square term and V in square term. It is 3 minus 2.25 and minus 2. So 3 minus 2.25 minus 2. That is minus 1.25 times V in square. Okay. Then I'll collect all the V in terms together. This is V in term, this is V in term, and this is V in term. That is minus 4.5 minus 7.5 plus 6.75 and plus 4. Okay, here I'm getting minus 1.25 V in. Now I'll collect all the constants together. Are you following? So it will be 11.25 minus 5.0625 and minus 2. So I am getting plus 4.1875. So this is the quadratic equation I am getting. Solve this in your calculators and let me know the answer. You have to be very careful in this. So you will get two values of V in, since it's a quadratic. One value I am getting it as 1.39736. Other value is V in is minus 2.3973. Are you getting these values? Yes or no? Tell me. Okay. So reject this value because V in cannot be negative. Select this value, V in. Okay, so V in is 1.3974 volt. Okay, now substitute this V in equation number 1. So we can say from 1 V out is equal to 1.5 times V in, that is 1.3974 plus 1.05. So how much is V out now? Calculate 1.5 into 1.3974 plus 1.05. How much it is? 1461. Perfect. Now we got this value called as 3. Okay. Now calculate VIL. V na V. VIL we already got, sorry. This is V in equal to VIL, right? So this is already we got. So we can say your V in, which is equal to VIL, is 1.39736. That is the value. You know what is the meaning of this? Let me just show it to you, just so that you will better appreciate that what we are doing. So if you plot this curve, V in versus V out, and you have this graph VTC curve, where is your VIL? Somewhere around here. Okay, so as you appreciate that this is 3.3 maximum value, this is V in equal to VIL. So how much is this point given by? 1.39736 and V in equal to, okay, and this is how much? V out. How much did we get? 3.1461. So as I've told you, for V in equal to VIL, output is just below VDD. So here is the proof of it. See, 3.3 it should be, it is just below that, 3.14. So this is the meaning of these answers which we are getting. For V in equal to VIL, how much is V out? 3.1461. So this is the value which we are getting. I hope you are understanding now. This is V out. Okay. Now on the similar lines, you have to calculate VIH. So are we ready for VIH? Okay. Let's begin for VIH. For VIH, we have the formula. Let me show it to you. This formula you might have to remember for VIH. This is we are solving for VIH, so we got this condition. Okay. This is the formula which we have to write. So let us write it down. V in equal to VIH. So we are doing calculation for VIH. So V in equal to VIH. What was the formula? VDD plus VTOP plus KR into twice V out plus VTON divided by 1 plus KR. So let's write it down. VDD plus VTOP plus KR into twice V out plus VTON, the whole divided by 1 plus KR. Okay, so this is the formula we get. Now we have to substitute the values. Let's call this V in only for time being, and at the last step we will call it as VIH. Okay, so how much is the value of VDD? 3.3. Let's write it down. 3.3. This is minus 0.8 plus KR is 2 into twice V out, we don't know. Remember, this V out it's different than this V out. This V out is associated with VIL. Okay, now what they are saying is, I'll let you know what is the meaning of that. 10 plus 1, okay, divided by 1 plus 2, that is 3. Alright, so here if you open the bracket, you will get 4 V out plus 2 plus 3.3 minus 0.8, so you'll get plus 4.5 divided by 3. Okay, so that is 4V out is equal to 3V in minus 4.5. So how much is V out given by? V out is given by 3 by 4 V in, which is 0.75 times V in, minus 4.5 upon 4, which is minus 1.125. Alright, so why this V out and the other one are not the same? Because right now we are going to find, let me show it to you in VTC curve. This is V out, this is V in, and the input point is different. That's why that V out is different. Here it is. So VIH is somewhere around here, VIH, and correspondingly the value of VO out is just above 0. So this V out and the earlier V out are totally different. This is V out for when V in equal to VIL, and this is V out when V in is equal to VIH. So this is what we need to find out now. Okay, so let's call this equation number, what was the earlier equation which we have used, 1 and 2, so this is 3, equation number 3. Okay, fine. Now we have to use this formula over here. We'll go back to the derivation 3.1. Now obviously it's difficult to remember this, alright. So what do we do is, in small steps we'll definitely directly determine the value of VIH. So yeah, let us do that. This is the background steps required, just as we did over here. In 1 or 2 steps we'll write down the formula. Okay, so these are the background steps. We write at V in equal to VIH, my output V out, this is my output V out, is slightly above 0. So V out is approximately equal to 0. So that means VDSN, which is equal to V out, is approximately equal to 0, and VDSP, which is V out minus VDD, is approximately equal to minus VDD. Okay, so that means this NMOS is in linear region, and since VDSP is almost equal to minus VDD, this PMOS is in saturation. You can work it out why it is in saturation. So here, see, this NMOS is in linear, PMOS is in saturation. Once we decide this, now we have to equate the currents. So ID P sat is equal to ID N linear. Okay, here it is. That is what we have written, right, in the derivation. Yeah, IDP sat is equal to ID N linear. Of course, we have to write some constraints. What are the constraints? We have written them before over here. Here it is, 4 of them. VGSN is V in, VDSN is V out. Let us write that again, just for our reference, once more time. VGSN is V in, VDSN is V out, VGSP is V in minus VDD, VDSP is V out minus VDD. Okay, so we have written these constraints. Now we expand this expression. This is Kp by 2 VGSP minus VTOP the whole square is equal to, this is Kn by 2 twice VGSN minus VTON into VDSN minus VDSN the whole square. Okay, now wherever we see VGSP, VGSN, VDSN, VDSN, we substitute these values over there, these values. Okay, so let's write that down. So this is 2 and 2 gets cancelled, and we also substitute inverter ratio KR is Kn by Kp. So Kn by Kp will come over here. So what is VGSP? V in minus VDD minus VTOP the whole square. Kn times twice VGSN is V in minus VTON. VDSN is V out. See, So into V out minus V out square. Is this clear to you? So this is the equation which we have to, don't remember, we'll derive it in one step. That is, are you following? So this we call this equation number, I think we can call it equation number 4. Okay, so this is equation number 4. Instead of remembering it, solve it in 1 minute time by doing this. That's it. Identifying the regions of operation. Alright, and from now on we will substitute the values and solve it. So let's start further. Let's proceed further. So it will be V in minus VDD is 3.3, VTOP is minus 0.8. So this will be plus 0.8, the whole square. This will be KN. This will be, sorry, KR. Sorry, this is one mistake. This is KR. KR is 2 basically. So this is 2 into V in. VTON is 1 volt. What is V out? V out is 0.75 V in minus 1.125. So V out is 0.7 V in minus 1.125. So we are substituting equation number 3 in equation number 4. Okay, so wherever we have this term, sorry, the V out term coming up, here is the V out term, here is the V out term, replace it with this. Got it? So we replace it with this 0.75 V in minus 1.125 minus 0.75 V in minus 1.125 the whole square. Alright, so we solve this quite patiently. So this we get V in minus 3.3 plus 0.8 is 2.5 square. This 2 will come, 2 into, we'll take it inside this 2 V in minus 2. Here we have 0.75 V in minus 1.125, and this we can expand it. How much is this? 0.75 a square minus b square. So it is 0.75 square, that is 0.5625 V in square. Okay, then minus twice 2ab. So 2 into 0.75 V in into 1.15. So how much is that? That is 1.6875. Please do this calculations. Plus b square, 1.125 square, it is 1.2656. Please check this calculations once. That is, we open the bracket here also. This is V in square. Okay, minus 2 times, this is 5 times 5 V in plus 2.5 square is 6.25. Okay, this 2 will take it over here, so we'll divide this by 2, and now we have to multiply these two. Okay, and get the equation. How much is this? 1.5 times V in square minus 2.25 times V in minus 1.5 times V in plus 2.25. So that is what we get over here. Then we'll write this as it is. This is minus 0.5625 V in square plus 1.6875 V in minus 1.2656. Alright, and now we club all the terms together. So yeah, if you want to write one more step, you can write that. So that will be 0.5 V in square minus 2.5 times V in plus 6.25 divided by 2 will be 3.125 is equal to 1.5 times V in square minus, if you club this together, you will get 2.25 plus 1.5. These are all the calculations which you have to take care. 3.75 times V in plus 2.25 minus 0.5625 V in square plus 1.6875 V in minus 1.2656. Now we club all the terms of V in together. Let's do that. This is V in, this is V in, this is V in. So what do we get? 0.5 minus 1.5 plus 0.5625. So we got it as minus 0.4375. Please check this square. Now we club all the terms of V in together. So minus 2.5 minus 3.75 and plus 1.675. So minus 2.5, then this plus 3.75, we take it over here, and this will be minus 1.676875. Here again we are getting minus 0.4375 times V in, and now we add the terms of constants together. So this and this. So it will be 3.125 minus 2.25 plus 1.2656. So we are getting around plus 2.1406. Please check the answer. Now we'll solve this quadratic equation. Solve this quadratic equation, you'll get two values of V in. Let me know the values. How much is the answer? Let me know. I'm waiting for you all to solve. You have to solve this very patiently. You cannot make a mistake over here. 1.76777, and other value is minus. So obviously which value you have to select? This one, because V in cannot be negative. So we can write over here V in is equal to VIH is equal to 1.76777, or we can call it 8 also. This is the correct answer. Now for this value of VIH, what was the value of V out? We have to calculate that also. We will do that. We can do that. So V out was what? Above formula. V out was 0.75 times V in, 1.7677 minus 1.125, right? Can you tell me the value of V out also? 0.75 into 1.7677 minus 1.125. How much is that? Someone? It is around 0.2. Yes or no? This is V in, this is V out. Let me show it to you what it means in the VTC curve here. So here is my VIH, and correspondingly what is the value of V out? 0.2 volt. Here it is. And what is the value of VIH? 1.7677. So you can easily see V out is just above 0. For when V in is equal to 1.7677, V out is just above 0. So this proves that we are going in the right step. Now at the last, we have to calculate the noise margin levels. So this is the numerical. This much computation is required for asymmetric, and it's very high chances that the numericals will definitely mostly come in the exams because of the numerical steps involved. Now we'll go to F, step number F, that is noise margin low is VIL minus VOL. How much is VIL? 1.39736. 1.39736 minus 0. So noise margin low is 1.3974 volt. Okay, and noise margin high is VOH minus VIH, that is VDD minus VIH. 3.3 minus how much is VIH? 1.76777, right? This 17 was missing over here. 777, yeah. So how much did we get? Noise margin high. Calculate this. 3.3 minus 1.76777. 1.5. Yeah. So this concludes the answer after finding the noise margin levels. So this is the level of CMOS inverter numericals. Okay. This is what we are going for. Are you able to follow? Now I'll give you another numerical. You try to solve that on your own. I'll give you the answers. Is that fine? I'll not solve the numerical, but I'll give you the answers. You solve it on your own. Will it do? Everyone? Yes? You're getting these answers. See, we meticulously solved this numerical. You'll get the correct answers. So we started with this. We found out VOH, VOL directly, KR dash. Then we found out VIL by this technique. It will take some time. CMOS inverter numericals will take some practice. VIH, we solved it using this technique. And finally we arrived at this step. Then noise margin levels. This comes normally for 10 marks. So numerical number 2. People, let's start. Write down. Consider a CMOS inverter with following specifications. Okay, so VDD is given as 3.3, VTON is given as 0.6 volt, VTOP is given as minus 0.7 volt, KN is 200 microampere per volt square, KP is 80. So we have to calculate the noise margins of the circuit of the CMOS inverter. So tell me, you want me to solve this fully or give you the answers? You will solve it on your own, or you want me to solve this entirely? I'll give you the option. Solving this entirely will take 20 minutes. Just giving you the answer will take you 2 minutes. Let me know. So I should write the answers only, right? Okay. So first, we'll discard whether it's a symmetric or a asymmetric CMOS inverter. So VTON is not equal to VTOP, correct? So CMOS inverter is not symmetric. That means we have to restart to the original, technique, the way we have done generalized. So VOH is VDD, which is 3.3 volt. Then we get VOL 0 volt. Then we you solve for VIL. So in solving VIL, you will also get the value of Vout for VIL. So this is 1.08 volt. You will arrive at 1.08 volt, and your Vout when Vin equal to VIL will come out to be, here I have not calculated, but you can calculate this number and let me know. Then E VIH, you calculate it, you solve this, and you will get the value of VIH as 1.55. So at what value you will get V out for this? So V out when V in is equal to VIH, here we got it as 0.27. Okay, acha, here we already got the value. Let me show it to you. It's 3.14. So you have to solve for these values which I'm marking in yellow color. For this you will require 20 minutes time. Meticulously solve the way I have done for the earlier numerical. Okay, and obviously after that solving for noise margin levels are quite straightforward. So noise margin low will come out to be 1.08 volts, and noise margin high will come out to be 1.75 volt. Alright, so solve this and get me these answers. I'll show you a different type of numerical one more after this, and then we'll end the lecture. Completed? Written the answers? But it's not as simple as it seems. You have to solve a lot of equations as we have done before. Now let me show you how it can be asked slightly differently. I hope you have written it down. Let me go to old papers, question papers. Yeah, these are some old question papers of BVLSI. See this type. This was the same numerical, right? I'll show it to you how frequently they are asking this. Can you solve this? Yeah, this is asymmetric design. So you solve this also. I think this is the same thing which I am using right now, right? Almost same parameters, yes. Yeah, it is. See? Yeah, this has come in exam before for 10 marks. So this is for 10 marks numerical. This is the same numerical which we have got it. Okay. And for the derivation part, see, they are asking resistive load. We have also done this. VOH, VOL, VIL and VIH. So yeah, we are on the right track. So let's see, go for another paper. 2017. So we have to search for VLSI paper. Yeah, here it is. See, I'll tell you the questions which were related to CMOS. So this is related to CMOS. VTC curve for CMOS inverter and explain all the regions in detail. Yes, we have done that. Derive the expression for VTH for a 2-input CMOS NOT gate. We will go over here. Okay. We'll see. Yeah, we didn't have a numerical here. Okay. Now we go to the next paper. I want to show you the variety since we have 2 minutes, 3 minutes more. Again, we have to search for BVLSI paper. I think this is the one, right? Okay. So here it's related to module number 1, enhancement type MOSFET. We search for a CMOS inverter numerical. See, they can ask you this type of question. See? Okay? These type of question. Determine the region of operation of PMOS and NMOS transistors as corresponding output voltages of a CMOS inverter for the following inputs. Alright, a long time back when we started with the CMOS inverter, I made you write one table. You remember that table, anyone? So we'll complete that table and we end the lecture for today. The table was showing what are the input and output levels for the CMOS inverter. Okay, so this question you can answer it with the help of that table also. So let me complete that table and then we will rest for today's topic. Is that fine? Yeah. So let us summarize that table now. So that was related to the VTC curve. So we have to draw the VTC curve for the one last time today. Alright. So these are the two critical parameters, VIH, VIL, and there is one more line is passing to the origin, V out equal to V in equal to VTH. So this is that VTH switching threshold. Then we'll determine the 5 operating regions now. This is region number VTO N, and here you will have VDD plus VTOP, and here you have VDD. So this is one region, this is the second one, here it is. So these are the 5 operating regions: A, B, C, D, E. Okay, and what was that table? We'll write the regions of operation, then we'll write what is the input level, output level, NMOS transistor status and PMOS transistor status. So region number A, B, C, D, E. Help me out in writing that quickly. So when region A, PMOS is in cutoff, NMOS is in linear. In region number E, NMOS is in linear and PMOS is cutoff. In region number C, both are in saturation. In region number B, NMOS is in saturation, PMOS is still in linear. In region number D, NMOS is in linear and PMOS is in saturation. We have derived all this. Okay, so we have written the table like this. Last time we have to complete this now. For A, region B, C. Okay, please complete this table. Let me connect it again. Yeah. Yeah, let me know now. For A, V in should be less than VTO N. And what is the V out state? Almost VDD. Okay, this is VOH actually, and this is VOL. This is actually VOH. So an output level is at VOH. B region is corresponding to VIL. Okay, and output is almost at below VDD level, so V out is almost high, approximately equal to VOH. In region number C, it is VTH. This is also VTH. Region number D, this is VI. Oh, this is VIL. Yeah, you have any query you can ask. VIH, this is VIH input, and this is low, almost equal to VIL. As you can see, output is low over here when input is VIH, and when input is greater than VDD plus VTOP, then my output is exactly equal to VOL, which is 0 for a CMOS inverter. So this was that table which I was talking about. Okay, so please complete this table. Anyone has any doubt? Okay, so with this table you have to explain this characteristics, as you can see very clearly. You explain the operation for a region number A, B, C, D, E. We have done that in the last few lectures. and we have been explaining that once and for all. So this table will help you out to write this answer more clearly. You have to justify why does the NMOS and PMOS work in these regions as shown over here. Okay, can I go back to the PDF? Yeah. So now the data is given in this form. Can you tell me how to solve this further? Anyone? Nothing. It's nothing new. You solve VTON is not equal to VTOP. Acha, tell me how to find KR over here. What is KR? Mu n Cox W by L of n, correct? Divided by mu p Cox W by L of P. That's it. So what they have given is, instead of asking you all Kn and Kp directly, what is Kn given by? You should know this, huh? Mu n Cox W by L. And what is Kp given by? Mu p Cox W by L of P. That's it. Now substitute these values over here. 60 into 8 divided by 25 into 12 and solve this. Okay, so what is the inverter ratio here? 1.6, right? That's it. And then all the steps are same. Are you understanding? And also, we have to find the value of switching threshold also. That is an additional thing. And we have written the value of switching threshold, right? The formula. So will you be able to solve this on your own? Everyone? Yes, no, what? Hello? This VTH formula was given to you. So we have to solve the switching threshold. Then noise margin high, noise margin low. Now this is the formula which we have. Let me just add this. We cannot add this image. Anyways, let me see if I can add this. No. Okay, anyways, this is the way we can solve CMOS inverter numericals. Let me check for one more. Yeah, see, same way. Now here they have found out the equivalent. Yeah, design the CMOS inverter is given over here. Determine the noise margin and inverter ratio for the design. Here it is given. So here symmetrical design is used. Here VM is nothing but VTH. I have shown that before. This is VTH. So it's a symmetric CMOS inverter design. VTOP, VTN, KP dash. Alright, we'll solve this. Okay, VTH is given as 2.5, VDD is 5 volt, VTP is equal to VTN mod of this, it's 1 volt, so it's a symmetric CMOS inverter. Okay, VIH is given to you, is equal to VOH is 5. Determine the noise margins, inverter ratio design for the design circuit. So VOL is how much? 0 volt. We know that. We have to only find the value of VIL. So we know that what was the formula for VIL, right? So we have to find the value of VIL and then design this inverter. So we'll see this somewhat later. Design of CMOS inverter is pending. Let me see another numerical. Yeah, here. Here they have asked a design for a NMOS inverter. Here you can see resistive load NMOS inverter. So this also you can do it. Determine the fall time. Yeah, here this is something different related to propagation delay. So here they have not given the formula for the, not asked the numerical on CMOS inverter. Let us see one more. June 2000 maybe. Yeah, see this again, asymmetrical design. So as you can see, every alternate paper we have been asked uh, uh, numerical on the CMOS inverter. So will you be able to solve these numericals on your own? Now that I have covered one numerical in detail, this is again asymmetric. This is symmetric or asymmetric design? Tell me. KR is not equal to 1, na? So this is asymmetric design. So you have to solve these and then the noise margin levels. Okay, and they have asked a numerical also on this, right? See, what do you mean by symmetric CMOS inverter? What is the value of the noise margin in terms of critical voltages? Draw resistive load CMOS inverter and derive its expression. So it's heavily intensive CMOS inverter related questions. All right. Okay, so I guess we stop the lecture now. So that's it for today. We have solved few numericals on CMOS inverter. In this lecture, we have solved numerical for CMOS inverter, which is not symmetric. And yeah, that's it for today. Next time, we'll start with some other topic.